In this video, I will be discussing about differential equations with coefficients linear in two variables. The standard form of a first-order differential equation having coefficients linear in two variables, which has a form a sub 1x plus b sub 1y plus c sub 1 quantity multiplied by dx plus a sub 2x plus b sub 2y plus c sub 2 times dy, which is equal to 0, where a's, the b's, and the c's are constants, then this is a differential equation that is linear both in the dependent and the independent variables. So to solve this particular differential equation, we need to consider the multipliers of dx and the dy, which is this one here and this one, which is a linear expression. And when you equate these two expressions to 0, you can have equations that represent two straight lines. So this a sub 1x plus b sub 1y plus c sub 1, which is equal to 0, represents a straight line. And also a sub 2x plus b sub 2y plus c sub 2 represents another straight line. So if this is the case, we can have two cases for the substitution to be used in solving this particular differential equation. So case number 1, when these two equations that represent two straight lines are equations of two non-identical parallel lines. So how do we know that these are two non-identical parallel lines? When the coefficients are proportional to each other. That is, a sub 1 over b sub 1 is the same as a sub 2 over b sub 2. So we say that the two lines are parallel. And that happens when your c sub 1 and c sub 2 are not also proportional. So in this case number 1, we need to use a substitution z, a new variable z, which is equal to a sub 1x plus b sub 1y, and the differential of this new variable z, which is dz, that is equal to a sub 1 times dx plus b sub 1 times dy. So this is just a differential of this substitution z. And the other case is when these two equations represent two intersecting lines with each k as their point of intersection, with c sub 1 and or c sub 2 not equal to 0. So how do we know that this represents two intersecting lines? When your a sub 1 divided by b sub 1 is not the same as a sub 2 divided by b sub 2. So if this is the case, we need to use the substitution x, which is equal to u plus h, where h is the x-coordinate of the point of intersection, and y, which is equal to v plus k, where k is the y-coordinate of our point of intersection for these intersecting lines. And also we need to find the differential of this x, which is du, because the differential of h is 0 because h is a number, is a constant, and the differential of y is dv because the differential of k is also 0 since k is a constant. And then to solve, we need to replace our variables x, y's, dx, and dy in the given differential equation by this substitution u plus h in lieu of x and v plus k in lieu of y and du in lieu of dx and dv in lieu of dy respectively. And usually the resulting equation after this substitution is a homogeneous differential equations. So we then proceed to the steps of solving a homogeneous differential equation. Actually, there is a third possible case here, which is similar to this case number 2, except that our C sub 1 and C sub 2 are both equal to 0. When this happens, the given differential equation reduces to a homogeneous differential equation of degree 1, which we have already discussed in the previous video under the topic homogeneous differential equation. So that is why we don't include the third case here. Now, to illustrate on how to solve a differential equation with coefficients linear in two variables, we proceed to this example number 1. Find the general solution of this differential equation. And you notice that the coefficients are linear in two variables because we have here 2x minus y plus 1, which is a linear in two variables, and also 4x minus 2y plus 3 is also a linear expression in two variables. And since we know that these 2 over the negative 1, which are the coefficients here, 2 and negative 1, is the same as 4 over the negative 2, which are the coefficients of this linear expression. So we say that this differential equation belongs to case number 1. So since this is case number 1, we need to use this substitution here. So we can use the substitution z, which is equal to 2x minus y. Actually, we can use also 4x minus 2y because they are proportionate to each other. So suppose we use this 2x minus y here as our z, then we can solve for our y. So y here is equal to 2x minus z. And since that is our y, we can solve for our dy here. And dy is equal to 2 dx minus dz. And then substituting this to the given differential equation, we have, so we will use this z here and this dy here in our given differential equation. And since our original differential equation is 2x minus y plus 1 times dx plus 4x minus 2y plus 3 times dy, which is equal to 0, then we can rewrite this given differential equation as 2x minus y plus 1 times dx plus 2 times the quantity of 2x minus y. So what I did is I just factor out the 2 in these two terms here. So we have this 2 times the quantity of 2x minus y plus this constant 3 here, and this is multiplied by dy. And for what purpose? So that we can replace this 2x minus y and also this 2x minus y by our new variable z. So instead of writing 2x minus y, we will write z. So this becomes z plus 1 times dx plus 2 times the z here, this one, plus the constant 3 times the value of our dy, which is this one here. So this is multiplied by 2 dx minus dz, which is equal to 0. So as we can see, we substitute 2x minus y by this z's here and also this dy by this expression here. So simplifying our differential equation, we have z dx plus 1 dx, if you distribute this dx to this binomial here, plus this binomial when multiplied by this binomial, we have 2z times 2 dx, which is 4z dx. And this 2z when multiplied by dz, we have minus 2z dz. And this 3 times 2 dx, we have plus 6 dx. And this 3 times negative dz is minus 3 dz here. So, grouping all the terms having the same coefficients of dx, we have this term, and also this term, and this term here. So we have z plus 1 plus 4z plus 6 quantity multiplied by dx. And the remaining term, we have minus the quantity of 2z plus 3 quantity multiplied by dz, which is equated to 0. And then combining similar terms here, we have 5z plus 7 times dx. And this will be subtracted by 2z plus 3 quantity multiplied by dz here. And you notice that this binomial is in terms of z. So this should not be a multiplier of dx. And to remove this binomial, we need to divide both sides of the equation by this binomial 5z plus 7. So what remains here is just dx minus 2z plus 3 divided by this binomial here. So we have 5z plus 7 times dz, which is equal to 0. And as you observe, this is already a separable differential equation. So therefore, we can solve this differential equation easily. We have all the z's in this term and the dx here in another term. And we notice that it is very easy to integrate dx, but we need some algebraic manipulation to integrate this fraction. And you observe that the numerator is of degree 1, which is of the same degree of this denominator here. So what we do is we need to convert this fraction to a proper fraction, because this is an improper fraction, by dividing this binomial by this binomial here. So dividing this numerator 2z plus 3 by this binomial here, 5z plus 7. So 2z when divided by 5z, we have 2 over 5. And then when you multiply back this 2/5 to 5z, we have 2z here. And 2/5 times 7, we have positive 14 over 5. So subtracting this one, 2z by 2z, we have 0. And this 3, when subtracted by 14 over 5, we have 3 minus 14 over 5. We can represent 3 as 15 over 5. And 15 over 5 minus 14 over 5 is the same as 1/5. So we have a quotient of 2/5 here and a remainder of 1/5. So therefore, we can rewrite this fraction as 2/5 plus the remainder of 1/5. And because this is a remainder, this will be divided by the divisor 5z plus 7 here. And this is multiplied by our dz. And of course, there is a dx here. And the whole thing is equated to 0. So, rewriting this complex fraction here, we have dx minus 2/5 plus 1 over 5 times 5z plus 7. And this is multiplied by dz here. And distributing this dz to this binomial here, we have dx minus 2/5 of dz minus 1 over the quantity 5 times 5z plus 7 times dz, which is equal to 0. And integrating each term in this differential equation, we have the integral of dx minus 2/5 of the integral of dz minus 1/5 of the integral of dz over 5z plus 7, which is equal to the integral of 0. And we know that if you let this denominator 5z plus 7 as your u, your du is not only dz, but it is 5dz. So we need to provide a 5 here to integrate this fraction. So we have the integral of dx minus 2/5 times the integral of dz minus 1/5 times the integral of 5dz. Instead of dz only, we have 5dz over 5z plus 7, which is equal to the integral of 0. And maybe you ask a question, where did I get the 5? Now, to neutralize this 5, I need to multiply here 1/5, because we know that 1/5 times 5 is just equal to 1. So as if I have done nothing to this term here. So we have the integral of dx, which is x, and the integral of dz, which is z, minus 1 over 25 times the integral of this, which is the natural log of the denominator 5z plus 7. And this is equal to the constant of integration c. And multiplying both sides of the equation by 25 so as to eliminate this denominator here, we have 25x minus 2/5 times 25, which is 10 here. So we have 10z minus this 1 over 25 times 25, which is 1. So this is 1 times the natural log of 5z plus 7, which is equal to the constant c, because a constant times another constant is still a constant. So substituting back our original variables, we need to substitute back our representation of z, which is 2x minus y. So we have 25x minus 10 times 2x minus y. And this will be subtracted by the natural log of the quantity of 5 times 2x minus y. So we have 5 times 2x minus y. And this is added to 7 here, which is equated to the constant of integration c. So multiplying this binomial here to their coefficients and adding that one to 25x, we have 25x minus 20x, because 10 times 2x is 20x, and then this will be added to 10y, because minus 10 times minus y is positive 10y, and this will be subtracted by the natural log of 10x minus 5y. And then we have a positive 7 here. And the whole thing is equated to the constant of integration c. So combining similar terms, we have 25x minus 20x. We have 5x plus 10y minus the natural log of 10x minus 5y plus 7, and this is equated to the constant of integration, c. And this is now our solution for this differential equation. Now, let's proceed to our example number 2. Determine the complete solution to this differential equation. So this is a differential equation which is having coefficients linear in two variables, because we have 2x minus y, which is a linear expression in two variables, and we have also 4x plus y minus 6, which is linear in two variables, x and y. So therefore, this is a differential equation with coefficients linear in two variables. And we noticed that these two linear expressions, when equated to 0, represent two intersecting lines, because when 2 divided by negative 1 is not the same as 4 divided by 1. So here, 2 divided by negative 1 is not the same as 4 divided by 1 here, the coefficients. Then we say this represent two intersecting lines. So next, we need to find the point of intersection. So for the point of intersection, we have 2x minus y when equated to 0, and we have 4x plus y minus 6, which is equated to 0. Then we can solve for the point of intersection by using elimination by addition. So 2x plus 4x is 6x, and minus y plus y is 0. So we have here minus 6, which is equal to 0. And therefore, we know that 6x is equal to 6. Therefore, our x is 1. So since our x is 1, we can solve for our y by substituting this x plus 1 to any of the equations. So suppose we use the first equation, 2x minus y, which is equal to 0, and our x is 1. So we have 2 times 1 minus y is equal to 0. So this is 2, which is equal to y. Therefore, we know that our y is equal to 2. So here, our point of intersection is at the point 1, 2. Therefore, we need to use our substitution for case number 2, which is x that is equal to u plus h. And we know that our h is 1, because we know that this number here is our h. And also, we need to use y, which is equal to v plus k. And we know that our k is 2, because this number is from here, which we know that this is our k. And also, we need to find its differential. So dx is equal to du, because the derivative of 1 is 0. And also the differential of y is dv here, because the derivative of 2 is 0. And substituting this one to the given dE, we have our original differential equation, which is 2x minus y times dx plus the quantity 4x plus y minus 6 times dy, which is equal to 0. We need to substitute our x's and y's by this one here. So instead of writing x, you will write its representation u plus 1. And then subtracted by y, which is v plus 2. So this is v plus 2 here. And this is multiplied by du, because dx is du here. And then added to the 4 times x, and our x is u plus 1 plus the y, and the y is v plus 2. So we have here v plus 2, and then subtracted by 6 quantity multiplied by dy, which is dv here. And then this is equal to 0. So simplifying our expressions here, we have 2u plus 2 minus v minus 2 times du. And this is added to 4u plus 4 plus v plus 2 minus 6 times dv here. So combining similar terms, we have 2u minus v times du, because 2 minus 2 is 0. And this is added to 4u plus v times dv, which is equal to 0, because 4 plus 2 is 6, and when subtracted by 6, the result is 0. And we notice that this is a differential equation that is not a separable differential equation. However, we observe that this is a homogeneous differential equation, and the solution for this homogeneous differential equation can be solved by the method we have learned from our previous video, which is about solving a homogeneous differential equation. And since we notice that this coefficient of du is slightly simpler than the coefficient of dv, then we use our substitution u, which is equal to zv, because our differential equation is in terms now of the variables u and v. So we will introduce here a new variable z to be multiplied to v as our u here. And we know that the differential of our u is the differential of this product. So we have z dv plus v dz. But we should remember that we introduce here a new variable z. So z can be obtained by dividing both sides of the equation by v. So z is equal to u over v. So this is our value of z. So substituting this u and du to our new differential equation, we have 2 times the u, which is zv, minus the v times the du, and we know that our du is this one here. So instead of writing du, I will write z dv plus v dz. And this is added to 4u, and our u is zv plus the v, which is here, and this is multiplied by dv, which is equal to 0. And you notice that each term here in this equation has a factor of v. So to eliminate this v, we need to multiply both sides of the equation by 1 over v. So we have 2z, because the v here will be cancelled by this v, minus 1 times the z dv plus v dz. And this is added to 4z, because the v will be cancelled by this v here, and this is added also to 1, because this v will be cancelled by 1 over v times dv, which is equal to 0. And multiplying this binomial by this binomial here, we have 2z times z dv, we have 2z squared dv, and 2z times v dz, we have positive 2vz dz here. And this is minus 1 times z dv, we have minus z dv. And minus 1 times v dz, we have minus v dz. and this is added to 4z dv from here, and plus 1 dv. So combining similar terms, we have this term and this term and these two terms here. We have 2z squared minus z plus 4z plus 1 quantity multiplied by dv. And this is added by the remaining terms, which is 2v z minus v dz here. So combining these two terms, because they are similar terms, we have 2z squared plus 3z plus 1 times dv plus the v times 2z minus 1 times dz, which is equal to 0 here. And we notice that this is already a separable differential equation. So we will eliminate this factor of dv because this is in terms of z, and this v because this is a multiplier of dz, so that this one will be all z's and this one will be all v's. And that can be attained by multiplying both sides of the equation by 1 over the v here from here, and this one, which is 2z squared plus 3z plus 1. So this one will be cancelled by this one. So what remains is dv over v. And this is added to this quantity because this v will be cancelled by this v. So we have 2z minus 1 over the quantity of 2z squared plus 3z plus 1. And this is multiplied by dz here, and the sum is equal to 0. Now looking at this differential equation, it is very easy to integrate this dv over v, but this one needs an algebraic manipulation. So to solve this one, maybe is to make this denominator as a trinomial with a leading coefficient of 1. So we need to factor out the 2 here outside. So we have the integral of dv over v plus 1/2 of the integral of 2z minus 1 over this one, because we have factored out the 2 there, which is this one, plus 3/2 times z plus 1/2 dz, which is equal to the integral of 0. And we notice that if you let this denominator as your u, your du will involve the derivative of z squared, which is 2z, and the derivative of 3/2 z as 3/2 here. But we don't have a 3/2, so we need to provide a 3/2 in the numerator. So we have the natural log of dv over v, which is the ln v, plus 1/2 of the integral of 2z plus 3/2. And where did I get the 3/2? I need also to subtract 3/2 here. But remember, we still have a minus 1. So this is divided by z squared plus 3/2 z plus 1/2. And this is equated to the constant of integration, c. So grouping the terms, we have the natural log of v plus 1/2 times the integral of 2z plus 3/2, which we know that this is the derivative of this one here. So this is divided by z squared plus 3/2 z plus 1/2 dz. We separate this one as another integral. So this is plus 1 half, because we still have a 1 half here, times the integral of the remaining, which is negative 3 halves minus 1 over this denominator here, which is z squared plus 3 halves z plus 1 half. And this is equated to the constant of integration, c. So integrating this factor here, we have the natural log of v plus 1 half of the natural log of the denominator z squared plus 3 halves z plus 1 half plus 1 half times the integral of negative 5 halves, because minus 3 halves minus 1 is negative 5 halves. And this will be divided by this trinomial, which can be completed to form a perfect square trinomial. So to form, we have z squared plus 3 halves z plus the square of the half of 3 halves. And the half of 3 halves is 3/4. So we square this one here. And maybe you will ask, where did I get the 3/4 squared? So we need to subtract also 3/4 squared here, as if I have done nothing to the expression. So we notice that this one is already a perfect square trinomial. So we have the natural log of v plus 1 half of the natural log of z squared plus 3 halves z plus 1 half plus 1 half times negative 5 halves. And this is multiplied by the integral of dz over this square trinomial, which can be written as z plus 3/4 quantity squared plus 1 half minus 9/16. And this is equated to the constant of integration, c. So we have the natural log of v plus 1 half times the natural log of z squared plus 3 halves z plus 1 half minus 5/4 times the integral of dz over the quantity of z plus 3/4 quantity squared minus 1 half minus 9/16. But this 1 half can be expressed as 8/16. So 8/16 minus 9/16 is 1/16. And 1/16 can be expressed as 1/4 squared there. And we notice that here in this denominator, if this is our u and this is our constant a, we have a denominator that is u squared minus a squared. And we have also the differential of our u here in the numerator, because the differential of z is dz and the differential of 3/4 is 0. So we can apply our knowledge in integrating a fraction that is du over u squared minus a squared as the 1/2a, and our a is 1/4 here, times the natural log of our u, so our u is this one, z plus 3/4 minus a, which is 1/4. And this is also divided by our u again, which is z plus 3/4 plus our a, which is 1/4. And this is equated to the constant of integration, c. And of course, we still have the natural log of v here plus 1 half of the natural log of z squared plus 3 halves z plus 1 half. And we noticed that we can combine this trinomial into one fraction. So we have the natural log of v plus 1 half times the natural log of the fraction which is having a denominator of 2. So this is 2z squared plus 3z plus 1. And this is subtracted by 5 divided by 4 times 2, which is 8, and divided by 4 is 2. So this is multiplied by the natural log of z plus 1/2, because 3/4 minus 1/4 is 1/2, and this is divided by z plus 1, because 3/4 plus 1/4 is 1. So simplifying further, we can factor out our numerator, this trinomial here, as 2z plus 1 times z plus 1, and this is divided by 2 here, minus 5/2 times the natural log of the fraction 2z plus 1 over 2 if you combine this z and 1/2, and this is divided by z plus 1. So continuing this one in the next board, we have the natural log of v plus 1/2 times the natural log of the fraction, which is 2z plus 1 times z plus 1 divided by 2 minus 5/2 of the natural log of the fraction of 2z plus 1 divided by 2 times z plus 1, and this is equated to the constant of integration, c. So applying the properties of logarithms, we can use this 1/2 as the exponent to this fraction. So we have the natural log of v plus the natural log of the fraction of 2z plus 1 times z plus 1 divided by 2 quantity raised to the exponent of 1/2 minus this fraction, which can be used as the exponent of this fraction. So this is minus the natural log of the fraction 2z plus 1 divided by 2 times z plus 1 quantity raised to the exponent of 5/2, which is equal to the constant of integration, c. So applying the properties of logarithms, we have the natural log of v times the fraction 2z plus 1 times z plus 1 divided by 2 to the power 1/2, because this is a sum. So we have the natural log of the product of this v and this fraction here, and this will be subtracted by the natural log of 2z plus 1 over 2 times z plus 1 quantity raised to the exponent of 5/2. But this is a difference of two logarithms, so we can apply again the property of logarithms. We have the natural log of this v here times 2z plus 1 to the power 1/2 times z plus 1 to the power 1/2 over 2 to the power 1/2 here, and this will be divided the whole fraction by this one here. So this is 2z plus 1 to the power 5/2, and this is divided by 2 to the power 5/2 times z plus 1 to the power 5/2, and this is equated to the constant of integration, c. So we have the natural log of v times 2z plus 1 to the power 1/2 times z plus 1 to the power 1/2 divided by 2 to the power 1/2 times the reciprocal of this denominator. So we have the fraction of 2 to the power 5/2 times z plus 1 to the power 5 halves divided by 2z plus 1 to the power 5 halves here. And simplifying this fraction here, we have the natural log of v times 2z plus 1 to the power 1/2 for this factor here, and this is multiplied by this factor with a negative exponent, so this is minus 5 halves times z plus 1 to the power 1/2 for this term, and this will be multiplied by this factor here, so this is plus 5 halves, and also this is multiplied by 2 to the power 5 halves minus 1/2 there. So we have the natural log of v times 2z plus 1 to the power of 1/2 minus 5 halves, which is negative 4 halves, times z plus 1 to the power 1/2 plus 5 halves is 6 halves, and 6 halves is 3. And this is also multiplied by 5 halves minus 1/2, which is 4 halves, and 4 halves is 2, which is equal to the constant of integration c. So moving this factor to the denominator to make this exponent positive, we have the natural log of v times z plus 1 to the power of 3, and this is divided by 2z plus 1 to the power of 2. Of course, we have a constant of 4 here. And substituting back our original variables, we have our z, which is equal to u over v, and also our x, which is equal to u plus 1, and our y, which is equal to v plus 2. So therefore, our u is x minus 1. So this is the value of our u here. And our v is y minus 2. So this is the value of our v here. So substituting this u and v to our z, we have z, which is equal to u, which is x minus 1, and our v, which is y minus 2. So this fraction is the value of our z. So substituting this one to our answer, we have the natural log of v, and our v is y minus 2 times the z, and our z is x minus 1 over y minus 2 plus 1 raised to the exponent of 3 divided by our 2z plus 1, and our z is x minus 1 over y minus 2. So this is 2z and then plus 1, which is raised to the exponent of 2, times 4, which is equal to the constant of integration c. So simplifying our fraction, we have the natural log of y minus 2 times the fraction of x minus 1 plus y minus 2 all over y minus 2 raised to the exponent of 3 here. And this is divided by 2x minus 2 plus y minus 2 all over y minus 2. And the whole fraction is raised to the exponent of 2. And of course, this is equal to the constant of integration c. So we have the natural log of 4 times y minus 2 times the quantity of x plus y minus 3 to the power of 3 over the value of y minus 2 to the power of 3 divided by the whole fraction, which is 2x plus y minus 4 to the power of 2 all over y minus 2 to the power of 2. And multiplying this fractional numerator by the reciprocal of this fractional denominator, we have the natural log of 4 times y minus 2 times x plus y minus 3 to the power of 3 over y minus 2 to the power of 3. And this will be multiplied by the reciprocal of this, which is y minus 2 to the power of 2 divided by 2x plus y minus 4 to the power of 2. Now, simplifying our fraction, we have 4 times x plus y minus 3 to the power of 3 all over 2x plus y minus 4 to the power of 2, because this y minus 2 times y minus 2 quantity squared is the same with this denominator here. So this one cancels with the 2 factors in the numerator. And this is equal to the constant of integration, c. So raising both sides of the equation to e, we have 4 times x plus y minus 3 to the power of 3 over 2x plus y minus 4 to the power of 2, which is equal to the constant c. Because when a constant e raised to another constant c, the result is still a constant. So multiplying both sides of the equation by this denominator, we have 4 times x plus y minus 3 to the power of 3, which is equal to the constant c times 2x plus y minus 4 to the power of 2. And dividing both sides of the equation by 4, we have x plus y minus 3 to the power of 3, which is equal to the constant c times 2x plus y minus 4 to the power of 2. Because when the constant c is divided by 4, which is a constant, the result is still a constant. Thus, this is our answer for the differential equation in example number 2. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.